This is useful for certain operating system tasks that need privilege, but are working on behalf of the user application and don't require a completely separate context. Let's talk about what happens when a program's normal flow is disrupted. This is called an exception. Think of it as an unexpected event that the processor needs to handle immediately, almost like a fire alarm going off in a building. You have to stop what you're doing and follow a specific emergency procedure. When an exception occurs, the processor does two main things. First, it enters a specific processor mode, usually a privileged one like PL1 or PL2, which we discussed a couple of pages back. Why does it need to do this? Well, the code that handles the exception, the software handler, often needs special permissions to access system resources and fix the problem, much like only firefighters are allowed into certain areas during an emergency. Second, after switching modes, the processor starts running this special software handler, which is a piece of code written specifically to deal with that type of exception. What can cause an exception? The slide gives us a list of common types. A reset is the most fundamental one. It happens when the system is powered on or reset. Interrupts are usually signals from external hardware. For example, when you press a key on your keyboard or your network card receives a new data packet, it sends an interrupt to the processor to get its attention. Memory system aborts happen when a program tries to access a memory location it's not supposed to, like trying to write to a read-only area. Undefined instructions occur if the processor fetches a piece of data that it thinks is an instruction, but it doesn't correspond to any valid operation it knows. And finally, there are software-generated exceptions like supervisor calls, SVCs. These are actually done on purpose. A user application might use an SVC to request a service from the operating system, like opening a file. Similarly, secure monitor calls, SMCs, are used to call into the secure world, and hypervisor calls, HVCs, are for calling the hypervisor in a virtualized system. So, how does the processor know where to find the correct software handler for each different type of exception? This is where the exception vector comes in. An exception vector is simply a memory address. When a specific exception happens, the processor is automatically forced to jump to the address associated with that exception. It doesn't have to think about it. Its hardware is designed to go to that specific location. These vectors are all grouped together in one place called the vector table. As the slide says, it's a set of consecutive memory addresses, starting at what's called the exception base address. Each entry in this table points to the starting instruction of the handler for a specific exception. On the next page, we'll see exactly what this table looks like and what's stored at each of these addresses. When an exception happens, like the ones we saw on the previous page, the processor needs a way to stop what it's doing and jump to the correct software handler. How does it know where to go? It uses something called a vector table, which is essentially a map or a directory for exceptions. As you can see on the slide, the vector table has one specific entry for each type of exception. For example, the reset handler is always at the base address, which is shown here as offset 0x00. An undefined instruction, exception goes to offset 0x04, a supervisor call goes to 0x08, and so on. Notice how each entry is exactly 4 bytes apart. Now, here's a very important and unique detail about the ARM architecture. In many other systems, a vector table contains the memory addresses of the handler functions. But in ARM, the table entries themselves contain executable instructions. This is a key difference. So, when a data abort happens, the processor doesn't go to address 0x10 to read another address. Instead, it jumps to 0x10 and immediately starts executing whatever instruction is stored there. Because you only have 4 bytes for that entry, you can't fit a very complex handler, right? So, what do programmers usually put there? They typically place a single branch instruction, which immediately jumps to the full, more detailed exception handling routine located elsewhere in memory. This single entry can hold one 32-bit ARM instruction, or if the processor is in thumb state, it could hold two 16-bit thumb instructions or one 32-bit thumb 2 instruction. A special bit, the T bit in the System Control Register, SCTLR, tells the processor whether to interpret the code in the vector table as ARM or thumb instructions. Another powerful feature is that the location of this entire table isn't fixed. The vector table's base address is configurable. At reset, the processor can be configured to look for this table either at address 0x0, which we call low vectors, or at a very high memory address, 0xFFFF0000, known as high vectors. This is controlled by the V bit in the SCTLR or sometimes by an external hardware signal. Why is this useful? Well, you might have read-only memory, ROM, at address 0 at boot, but later you might want to remap that area to RAM and move your vector table. This high/low vector option gives you that flexibility. Furthermore, newer versions of the architecture and features like the security extensions provide even more advanced ways to place the vector table using special vector base address registers, giving developers even more control over the system's memory layout.